All right, let's take a look at section 15.7, which will cover triple integrals. So just the one learning objective this time, we're going to practice evaluating triple integrals over general regions. Just a couple of theorems to talk about first. One of which says that if we have a closed and bounded region E in space, this being some three-dimensional region E, we can calculate its volume with the triple integral over E of dV, where dV is, as opposed to like dA or dx, dV will be the infinitesimal change in the volume at whatever point we're located at. The second theorem is the return of Fubini's theorem, just this time for 3 dimensions. That says that if we have a continuous function on a rectangular box region, so each of x, y, and z are just bounded by constant numbers, will give us a rectangular box somewhere in space, then the triple integral can be calculated with the iterated integral of 3 variables, so 3 integrals, one for each of x, y, and z, where we can do that iterated integral in any order. Since there are 3 variables, that being x, y, and z, we take 3 factorial, 3 times 2 times 1, we get 6. So there are 6 possible orders for this integration to happen in. 3 choices for the first integral we want to do, which leaves only 2 choices for the second, and then only a single choice for the third. And we can go in whatever order we want, so oftentimes it'll be helpful to rearrange an integral to go in an order that's more favorable to us. But let's just take a look at an example. So evaluate the triple integral of x, y, z plus 1 dv, where E is the region given here. X goes from 1 to 5, y from 2 to 3, and z from -2 to 0. So x and y and z. So if we set up that iterated integral, we will go from, let's actually zoom in a bit here. We still have x, y, z plus 1 hanging out in the middle, but we'll go from 1 to 5 on the x values. We'll go from 2 to 3 on the y values, and from -2 to 0 on the z values. And since we evaluate these integrals in the order of inside out, dz is going to go first, just based on how I wrote the integrals out. dy goes second, and dx goes third. So we just want to make sure that our integrating factors match up with the bounds that they correspond to. So first up, we're doing that integral over z. We'll still have 2 integrals left after we do this. So this will go to xy z squared over 2 plus z. If we plug in 0 for either one of those, we're going to end up with 0. So don't need to worry about that one. If we do z squared, or plug in -2 in for z, -2 squared will be 4. 4 over 2 is just going to be 2. So we'll end up with a -2 xy minus z. And so if we plug in -2 there, that'll be minus a -2, so plus 2. If my math works out, we still have dy and dx happening after that. Dx still from 1 to 5, and dy still from 2 to 3. One more integral to go, or rather 2. But after we do the y integral, we'll only have 1 left. So what do we get if we integrate this thing with respect to y? Well, we'll get -2xy squared over 2, so just -xy squared plus 2y, and we're going to plug in 2 and 3. So if we do 3 squared minus 4 squared, 9 minus 4, that's 5. So now we'll have negative 5x plus something that we get when we plug in the 2 and 3 into 2y. That difference there is going to be just 1. So we'll have 2 times 3 is 6, minus 2 times 2 is 4. So 6 minus 2, that should be plus 2, leaving just our dx remaining. Or integrating from 1 to 5. And if we plug all that in, we'll end up with negative 5x squared over 2 plus 2x. So let's see what happens when we plug all that in. So we'll have x squared, and we're plugging in 5 and 1. So 25 minus 1 will be 24. So negative 5 over 2 times 24. Let's put that part in purple because it's coming from our x value. Plus 2 times x. I will plug in 5 and plug in 1 and take the difference. 5 minus 1 is 4. So what happens if we simplify all of that? 24 over 2 is 12. So negative 5 times 12 is going to be negative 60. Plus 8 should be negative 52. And that matches what I calculated beforehand, so I'm pretty sure I got all those numbers right. Okay, let's take a look at our next example. So we're going to do a triple integral of x dv, where d is the region in the first octant bounded by the plane x plus y plus z equals 1. So for starters, the first octant, kind of like the first quadrant, except it's in 3 space. So we have 8 instead of 4, so they're octants instead of quadrants. First octant means that all 3 of x, y, and z are positive. So we're going to be bounded by x, y, and z must all be greater than or equal to 0, because that keeps us in the first octant, and also the plane x plus y plus z equals 1, pictured here in the diagram labeled figure 5. If we look at where that plane intersects the octant, the first octant, we'll have points at 1, 0, 0, 0, 1, 0, and 0, 0, 1. Highlighted, of course, here, here, and here. And then the lines that connect each of those points together. So some sort of a pyramid-looking region. So what do we want to do? We want to turn this thing into an iterated integral. So why don't we start by solving that plane for z? Doing so should give us z equals 1 minus x minus y. And then we'll take the projection of this region into the xy plane, and we'll look at the bounds that happen there. So if I draw a quick set of coordinate axes, I'm only going to need the first quadrant, because I know I'm going to be projecting from the first octant into the xy plane. Doing so should give us this region, where y, we're at the point 0, 1, and at x, we're at the point 1, 0. And just projecting that thing into the plane, we have this shape that we're going to want to integrate on. And we can just set up some bounds here. How about y equals 1 minus x, being that diagonal line, the bottom being y equals 0. And then that'll leave x free to float between 0 and 1. So if we put all those colors together, we should end up with a series of integrals that we can take. The one that I haven't listed already was the one that we said where we have to be bounded by the first octant, which means that the bottom value in our z integral should be z equals 0. So we'll be bounded by the plane z equals 0. Now, this is just one of 6 possible orders that we could take, and any one of them would be valid. So you're free to experiment or do whichever one you think is best. But I'll go ahead and tackle this one. So we are looking for a triple integral, or rather an iterated integral of 3 variables, where if I leave myself just enough space to write everything down, z is the one that we did first. So we'll want to go z from 0 to 1 minus x minus y. Y was the second one that we solved for. So y is going to go from 0 to 1 minus x. And x was the third one, so it's going to go from 0 to 1. And then we'll keep the same integrand on the inside, which I believe is just the function x dv. But of course, we'll want to rewrite dv in the order that we're going to be taking these integrals in. So we said z first, followed by y, followed by x. And we'll integrate this thing. Doing so. First, we're going to be integrating with z. So that integrates to just xz. Z goes from 0 to 1 minus x minus y, which means this should just be x times 1 minus x minus y. So far, so good. Keeping that same order, y is next. We go from 0 to 1 minus x. Z was third, or x was third. Dx, so 0 to 1. So let's integrate that thing with respect to y. Doing so, what'll we get? Well, looks like we can simplify this thing to x minus x squared times y minus x y squared over 2. Where those y's need to be evaluated from 0 to 1 minus x. Go ahead and throw our x bounds back in, 0 to 1 with a dx there at the end. So I just multiplied that x through and then separated out in the pieces that have a y versus not having a y. And we'll plug in our boundaries and see what we get. So one more step before we get to our answer. X still going from 0 to 1. On the one side, if we plug in 0 for y, everything's going to be 0. So we don't need to worry about that part. We just have to worry about that 1 minus x. So we'll get x minus x squared times 1 minus x minus 1 minus x squared. Well, doesn't seem too bad. Let's just multiply that out. X minus x squared times, we'll have 1 minus x minus x times, we've got 1 minus x squared. Nope. 1 minus x squared. That's over 2 dx. And figure out what the heck this thing comes out to. Well, we could factor a 1 minus x out of that mess. Will that get us anywhere? Yeah, that won't be too bad. X minus x squared minus x plus x squared over 2. Actually, yeah, that worked out to be kind of nice, didn't it? So if we just, for a moment, grab this 1 minus x here, pull it out, factor all of that. We got rid of this power of 2. So we're just here. Scrunch this thing back together. Dx is there. Yeah, we've got x minus x squared minus x plus x squared, but that part's over 2. So it looks to me like that thing should just simplify to x minus x squared over 2. So let's do that. X minus x squared over 2. And now we'll have to multiply our 1 minus x into that, but that doesn't look so bad. Multiplying x minus x squared times 1 minus x, what are we going to get? Let's drag that down here for a moment. On the one hand, we'll have x minus x cubed minus x squared and lastly, wait, hold on a second. That should have been a minus x squared. Yeah. And then we have negative x squared times 1. So minus x squared again. And then negative x squared times negative x should be minus x cubed. All of that over 2. And so finally, let's take the extra step of simplifying that inside piece. That'll be minus 2x squared. I'm pretty sure that actually came out to be a plus x cubed because it was a negative times a negative. Okay, cool. So now we should just be able to evaluate this integral. And that one does not look too bad. Oop, x squared. There we go. So this should be 1/2 times x squared over 2 minus 2x cubed over 3 plus x to the 4th over 4, evaluated from 0 to 1. So that'll be 1/2 times 1/2 minus 2/3 plus 1/4. What do we get if we multiply that all together? Half plus 1/4 is 3/4. 3/4 minus 2/3. Let's see. 3/4 is 9/12. So 3/4 is 9 over 12. 2/3 would be 8 over 12. Subtract those two and we get just 1 over 12 times 1/2 is 1 over 24. Cool beans. Right, and let's check out the triple integral example 3, where I'll just kind of bring this picture in for a second. We want to find the volume of the solid enclosed by the paraboloids y equals 2x squared plus 2z squared and y equals 5 minus 3x squared minus 3z squared. And the way that we're going to want to do that is going to be kind of similar to what we have in figure 3, where it's going to be similar to the process, but I should point out that the figure that's here, this is not exactly our shape. not exactly our shape. Right, or we just have some general, in the diagram, there's just some generalized region E that's being projected into the XZ plane to find an area region D rather than a solid volume E. So if we project E into the XZ plane, we can then first do a single integral over Y and then have a double integral on a region D, which we'll just fall back on methods that we've already looked at. So step one in this example is going to be to basically project the region or the solid that we have into the XZ plane. So it'll help us to start by saying that Y needs to be between the two paraboloids given. And a few sections ago, we said that if we were interested in finding a projected image, it was usually easiest to just find the projection of the boundaries, which means that we're going to want to find the intersection of these two paraboloids and then use that to set up the boundary for the region D that we're going to want to look at. So if Y is in between those two things, and they are two paraboloids that are Y equals something, we ought to be able to just set those two things equal to each other. So we'll have 2x squared plus 2z squared equals 5 minus 3x squared minus 3z squared. Put all our x and z on the same side to get 5x squared plus 5z squared equals 5. Or more simply, x squared plus z squared equals 1. So that's going to be the projection into the XZ plane. So if we just put some coordinate axes up here, we'll call that X and Z. Our shape, I think, should just be a circle of radius 1. Let's try and center that a little bit better. Cool, so x squared plus z squared equals 1. And our region is the interior of that circle. And what did we say that was? Based on our diagram, this should be region D. So maybe I should have put this all in yellow instead of in green. Oh no, come back. Nah, whatever. Green is going to be fine. I'm going to use yellow when I do the integration. In fact, I've already used yellow. I said that's why. So we now could set up a series of boundary equations to express D. So for example, I could say Z equals, or let's actually use the colors that we normally go with. Z is magenta. Z is plus or minus the square root of x. Ooh, nope, try that one more time. 1 minus x squared, positive for what would be the top half of that circle, negative for the bottom half of that circle. So we'd have our two boundaries for Z. Then that means that x just goes between 0 and 1. So x equals 0, 2x equals 1. And we could set up our integral and do it that way just fine. However, it'll probably be way easier to do the second part of that integration in polar coordinates, which is what we're going to end up doing. So it doesn't matter that it's x squared plus z squared equals 1 instead of x squared plus y squared equals 1. We can set up polar coordinates in any one of the three planes that we want to. And that's what we'll do here. So let's set up what that integration should look like. I'll start with saying that we just are going to have a double integral over the region D, and then a triple iterated integral where we know what y needs to go between. The bottom part of that paraboloid is going to be 2x squared plus 2z squared. The top paraboloid is going to be 5 minus 3x squared minus 3z squared. And all we want to do is integrate dv, which if we put these things in the correct order should be dy. And then for sake of argument, we said z would be second and x would be third. And yeah, this is 1 times all of that. If we do that first integral for y, we should get, still going over the region D, we'll have just, that thing integrates to y, so it's just the top piece minus the bottom piece, which comes out to 5 minus 5x squared minus 5z squared. And then we said dz dx. But here's where we're just going to change those things around and instead integrate this thing in polar coordinates. So if we do that, we should give some labels here for theta and for r. How about we do theta in green? We're going to go all the way around the circle. So it should be 0 to 2 pi. We have a circle of radius 1. So r can go from 0 to 1. And this thing should be 5 minus 5r squared. Since x squared plus z squared is going to be equal to 1 in this particular set of polar coordinates, because we're just using z instead of y. And we're going to want to multiply in our dA for that region R. And don't forget that in polar coordinates, if we're going to replace dA, we need to multiply by r times dr and d theta in whatever order we want to go in. So that r is because of dA. So don't forget that from the last set. I'll just make a quick note over here. dA equals r. The next part is supposed to be in pencil. dr d theta. Just to highlight where that r comes from. What order did we say to go this? We're going to go this in. R was first, it looks like. So dr and then d theta. So what happens next? We've got 5r minus 5r cubed, which we can, we'll integrate that thing in a second. But also notice that there's no dependency on theta in this integrand, which means I could just separate out these two integrals and then multiply them together. So this thing is going to come out to 2 pi for the theta integral times whatever we get when we do the r integral. So 5r minus 5r cubed should go to 5r squared over 2 minus 5r to the 4th over 4. Maybe I'll make that parenthesis a little bit bigger. And this thing is being evaluated from 0 to 1. So we've got still our 2 pi times, if we plug in 0, it's 0, so we don't have to worry about that. Plugging in 1, 5 over 2 minus 5 over 4. Pretty sure that simplifies to just 5 over 4. Yeah, 5 over 2 minus 5 over 4. We'll simplify to 5 over 4. And if we multiply that together, 5 pi over 2 is what we end up with. All right, and now for example 4, we're just going to consider an integral that has bounds for z, then y, then x. If I start from the inside and go back out, of some function f. I'm not going to care about what the function is for right now. My only goal for this example is going to be to rewrite that iterated integral using all 5 different orders of x, y, and z. I just said 5 different orders because we already have the first one written out. So again, there should be 6 in total, but we already have 1, so we're going to do the other 5. So we want to figure out how to do that. So the first part that I did, I have drawn what I hope is a reasonable freehand of the coordinate plane, or at least the first octant again, because it looks like that's the part that we're going to be looking at. I traced out the lines x equals 1 and y equals 1 because I think that they're going to help. But my goal is going to be to sketch this region and then use that sketch to reorder each of these pieces. So let's take a look at the order we're going in. It's z, then y, and then x. So x, I've got the 0 to 1, so it means I'm really just going from the origin out to the line where x equals 1, which is just what that light gray line is going to represent. So next, let's take a look at what's going on in the xy plane. I have 2 equations for that are in terms of y equals. I have y equals 1 as the rightmost boundary, and I have y equals the square root of x as the leftmost boundary. So if we attempt to draw that shape in the xy plane, I'm just going to try to draw a square root function. Hopefully it looks about like that. Y equals the square root of x, and the line y equals 1. Next, we'll want to take a look at what's going on in terms of z. So z, is bounded on the bottom by the line, or by the plane z equals 0, and its upper bound should be the plane z equals 1 minus y. I'm just going to sketch in the part that's in the yz plane. So if we start up here at z equals 1 and just draw in the line that we get there, freehanding it, I get a shape that looks about like that. So now I've got that's going to be our zy plane. So we've got this shape right here is our backdrop. I've got this shape here is our floor. And I want to just connect these pieces together, which I suppose I'll do with a red line. And it should kind of follow that square root of x equation, but be in the plane z equals 1 minus y. So if we do that, I think our shape is hopefully going to be about like this. Or if I then erase my 2 backdrops and focus on the shapes that we're left with, I have the top traced here in magenta. Hopefully this is easy enough to read. And then I have this other curved shape that's going from the origin out to the point where x and y are both equal to 1. So you end up with that shape that's right there. And was red the best choice? Red usually shows up. Hopefully it still kind of will here. But that's about roughly what our shape looks like. If we take a look at the computer-generated shape we've got over here, labeled number 1. Maybe that one's a little easier to sort of recognize what we're doing. The next step that we're going to take in this process is going to be to project this shape into each of the 3 coordinate planes to try and get a look at how we're going to need to change these integration bounds. So in step 2, I have an example of showing a projection into the XZ plane. We probably aren't going to start with the XZ plane, but that's the one that just was easiest to show. So it's the one I did. Anyway, back over here to our shape. Let's see what happens if I grab this red line and change it to blue. Does that help it show up any better? Actually, I think it kind of does. Let's put it in blue. And maybe it'd also help if I could color in the lines a bit better. That also didn't show up great. Maybe some magenta slashes. Sure, I don't hate it. Let's try working with that. Okay, so given where all that stuff came from, I'll re-highlight, that was in terms of Z. This line, the yellow lines came from the Y equals stuff. And we know that X is going from 0 to 1. So if I kind of trace back through what my steps were, starting with 1. So step 1, I wanted to draw out my X bounds because that was the outermost integral. And I also put up the XY plane. Draw XY plane. X equals 0, X equals 1. I suppose are really the most important parts that I was doing there, since I know that that's where the X bounds are going to be. I did that part very lightly because I know that's not going to end up being my overall shape. Just gives me an idea of how wide the thing's going to be in the end. The second step, I drew out the lines that were on inside the middle integral. So we wanted to draw y equals 1 and y equals square root x. Which means then that step 3, I wanted to draw out my final integral piece. So z equals 1 minus y. And then fourth, I'm using that blue line to then connect the planes. Connect the planes. And roughly that's about how I got the shapes that we were after. Okay, so what's next? Now that we have our 3D shape, we're going to need to look at projections of this shape into each of the other 3 coordinate planes. The easiest one to do is going to be to switch the order of the outer 2 most integrals while leaving the inside one the same. And since my outer 2 variables are y and x, I'm going to start by projecting this thing into the xy plane. So scroll this down a bit. We are going to do dz first, followed by dx and then dy. So that's going to be the new order, which means projecting into the xy plane. So in the xy plane, We had the line y equals 1. And we had the line y equals the square root of x. And then this is our projection into that xy plane. And our goal is just going to be to reorganize this shape into something where we can set our boundaries up for x equals something instead of y equals something. So we also have the point 1, 1 right there. Probably is going to end up being important. But let's rewrite our boundary equations. So instead of y equals x, we'll want x equals y squared. And for the left turn piece, right along here, we're going to want the line x equals 0. So if we're reorganizing that integral to be in terms of dz, dx, dy, our triple integral should look like this. Probably I'm going to need to give myself a little bit more space between the second and the third. So y is now happening last. It's going to go from 0 to 1. X is happening in the middle, and it should be going from 0 to y squared. And z, we left alone. We didn't need to change this one around. So we can still go from 0 to 1 minus y. And then everything else on the inside we leave alone. Well, rather the function we leave alone, function of x and y and z. I'm probably just going to start abbreviating that just to f rather than the whole piece. But we were still doing z first, but now we're doing x second, and we're doing y third. Okay, let's cordon that off. Bring up my ruler real quick. Draw a dividing line right there. Because now we're going to try this again. Okay, so let's now switch and do an integral where we'll start with y rather than with z. So dy first, and then let's do dx dz. We're going to have to do both, but we just have to pick one to start with. So we'll go in this order. If we're doing y first, that means that we're now going to want a projection of this thing into the xz plane, which is the one shown by the computer-generated drawings I had up a little while ago. So we'll put x here, we'll put z up there. So it's going to be a bit of a mirror image from the one that we were looking at in this projection. So we're going to project in the VXZ plane. We'll have a shape that looks kind of like that. But if we just come up and look at the shape that we've got going on, we'll be projecting that yellow line, y equals 1, is just going to go into the line y equals 0, or z equals 0 down in the xz plane. And we're going to need to look at the projection of that blue line into the xz plane as well, which looks like it should come out to 1 minus the square root of x. So let's look at projecting that in. So we'll have yellow line, like I said here. The yellow line should project out to 1, and the blue line should project out to 1 minus x. And I guess we'll also be projecting that magenta line and back to be right there. So we kind of follow all of our projections through. This is the shape that we are looking at. How did we get that stuff? We are going to be using the equations. y equals square root of x, and y equals 1 minus z. Yeah, so if we started with, we had a yellow equation that said y equals the square root of x. We had another pink equation, which after rewriting says that, or no, even without rewriting, z equals 1 minus y, which in the blue line is now going to be 1 minus the square root of x. Right, if we just make a substitution there. If we put that part in yellow, sort of see where that's coming from. So that blue line is z equals 1 minus the square root of x. Also, that yellow line should now be z equals 0. But if we're doing x second, we're going to need to have equations for x that get us each of these lines. So along the left side, we've got the equation x equals 0. Along the right side, if we just rewrite that thing for x, which would be x equals 1 minus z squared. And then z will still go from 0 out to 1. As we look at this point right over here, that'll be the point, or rather, no, we're looking at z, so we're going to care about this point up here. X is 0, z is 1. So ultimately, our bounds should be, we have those x bounds already written out. Z bounds should go from z equals 0 to z equals 1. So if we put that triple integral back up, z from 0 to 1, x from 0 to 1 minus z squared. And finally, also a y boundary. If we come back up and just kind of look at where that y was coming from, it looks like it's going to be bounded below by the square root of x. And it'll be bounded on top by the plane y equals 1 minus z. Where we have our function f of x and y and z in terms of dy and then dx and then dz. All right, so to quickly recap, I knew I wanted to do y first, which meant projecting into the xz plane. Once I had my projection into that plane, I know I'm doing x second. So I'm going to want to write my boundaries in terms of x, or x in terms of z, x is a function of z. And then z is last, so we'll just go between its smallest number and its largest number. And then for the y functions, I was looking at I needed to rewrite the original equations that I had back in this 3D diagram to be in terms of y equals something in terms of x and z. So y needs to be functions of x and z. So I've got y equals the square root of x, was this equation down here. And then I was using z equals 1 minus y, just rewriting that for y equals 1 minus z to be the plane that's on top, the plane that's shaded in magenta. I guess it's sort of the rightmost face, but yeah. All right, so that was the next order. We did dy, dx, dz. So next, we might as well do dy, dz, dx. Draw another sort of boundary line here. So dy, then dz, then dx. And this one, we already have the projection we need. So we'll look at doing those same pieces. The y part won't change. It'll still be square root of x up to 1 minus z. It's just the z parts that we'll want rewritten. So if we check back out that equation that we had, we already had them expressed in terms of z. Z equals 0 on the bottom, z equals 1 minus x on top. They are yellow and blue in that picture, but I'm going to change them to magenta in this integration. 0 on bottom, 1 minus the square root of x on top. And that means that x just gets to go from 0 to 1. Our function f of x and y and z in the order that we wanted. dy, then dz, then dx. One last dividing line. So now we need to switch and do x first. Dx, let's just go in order. Dx, dy, dz. So if we're doing x first, we're going to need the final projection into a plane. This means we're going to want to project our original shape into the YZ plane. So we come up and take a look at that projection. That one doesn't look too bad. It's just going, we already have a shape that's in the YZ plane, and that's just going to be a triangle. So if we project that shape back in, where we'll have y down here, and z be the vertical axis, we've got a magenta line right here. Where that magenta line is the equation z equals 1 minus y. So if we just rewrite that line to instead be a function of z, y is equal to 1 minus z, same one we've been using earlier. And its bottom boundary should be, let's try that one more time. Its left boundary should be y equals 0. Its bottom boundary would be z equals 0. So for this triple integral, we'll have these three iterated integrals, because that's what we're doing here. Z we know is going from 0 to 1. Y should be going from 0 to 1 minus z. All right, so now we need finally, we need a boundary for the x values. So if we come back up to our three-dimensional shape, we're going to be looking at where x falls between the plane x equals 0 is the YZ plane. So that'll be the furthest back part. So we're going to be using x equals 0. That's this plane. On the back, it is the YZ plane. And it's going to come out to the function right now that is y equals x, y equals the square root of x. So if we were to just rewrite that piece, that would be x equals y squared. So for the final boundary on x, we want to be going from the plane x equals 0 to the curve x equals y squared. F of x, y, and z in terms of dx, then dy, and then dz. So now we just have to do the final iteration. where we're going to keep x in the same spot. It's first, f of x and y and z, dx there. But now I want dz next and dy last. But we already had these bounds written out in the picture above. Z needs to go from 0 to 1 minus y. And y will go from 0 to 1.